Hi everyone, I'm Nathan Matsuda, and I'm here with my co-author, Alex Shapiro, and we're presenting Realistic Luminance in VR. This project sets out to find preliminary answers to these questions. First, if we're trying to recreate the real world in a virtual environment, what sort of luminances would we expect to see? Then, how can we recreate those realistic luminances in VR given hardware limitations? Finally, if we show realistic luminances to viewers, how do their perceptions in VR differ from their perceptions if they were looking at a traditional display like a television? Okay, so let's look at the first part of this. If we're recreating the real world in a virtual environment, how bright does it actually need to be on an absolute scale? So here's a photo that I took in my office. This is, of course, a low dynamic range image. The bright values are clipped, but I had a luminance meter on hand and I actually measured a few different parts of this scene. So, for example, this sort of medium white spot on the curtain is about 86 nits. Bright part of this LED light is over 11,000 nits, almost 12,000 nits. And of course, the sky here, which is not even, this isn't even the sun or anything, this is just the sky, is about 43,000 nits. So this is a broad range within this, just a small portion of the field of view, which kind of hints at the dynamic range that we actually see in the real world. Now, if we look at display hardware on a linear scale, we see that on the far left there, current consumer VR headsets can usually recreate about 100 nits. A really nice HDR TV can reach a peak brightness of around 1,000 nits. A good frame of reference here is a 60-watt equivalent light bulb. Is around 16,000 nits. And then, of course, once we start talking about outdoor luminances, like something that's in direct sun, a sidewalk, for example, we're looking at somewhere around 150,000 nits, although that varies widely. What we've done here to enable this project is to build a prototype hardware that we called Starburst that achieves over 20,000 nits peak luminance. So I'll briefly describe how we built this hardware before we get into how we used it. This has been an ongoing project for several years now, but the current form, the current architecture of this headset really came together about a year and a half ago. This was a benchtop version that I had put together, and it's basically two LCDs, a color and a mono LCD with a really bright backlight, a big chip-on-board LED, which is then cooled and has a big power supply. We brought in our co-author and hardware engineer, Clinton, who did a lot of work to eventually package it into this form factor prototype, it's not fully head mounted in that it's too heavy to actually hang on your head, but you can hold it up like a pair of binoculars and use it as if it were a normal VR headset. It has 6 degrees of freedom tracking, and you can move around in a relatively natural way. So inside of this thing, there's quite a bit of real estate dedicated to cooling, and that's because we have these big LED backlights that I showed on the benchtop setup. It's an LED array that excites phosphor to produce broadband white illumination, and it's very bright. Because we want to maintain as much of that brightness in the eye box for the viewer, we have some illumination optics that collect stray light as much as possible and direct it through first a color LCD, which is stacked directly behind a monochrome LCD, and these two together produce increased contrast, whereas if you used a single LCD and used such a bright backlight, your black levels would be very high and you would have a very low quality image. And then we have a standard VR eyepiece. Now this big mesh here is part of the heatsink, as well as 2 large aluminum blocks that sandwich the 2 LCDs together, and the air passes through all of that heatsink material and is pulled out with these cooling fans, which is necessary because the LEDs put out a lot of heat and the LCDs are quite sensitive to temperature. And then finally we have an off-the-shelf positional tracker attached to the front of the headset to provide a full VR experience. So this is what it actually looks like inside the headset. This is a through the lens view. And again, because we're looking at this with a low dynamic range camera, what I'm going to do is pause it. And then I'm going to stop the camera down so that you can see how those highlights are preserved. So here we go down 5 stops, and you can still see that those highlights on those spheres are resolved rather than being fully clipped. Whereas if I switch to just a single LCD low dynamic range mode, the light and the highlights are clipped at this medium gray, and they don't contain all that extra information that you get by having this dual modulation and the bright LED light. Now again, we have this pair of LCDs, color and mono, and you can see here, I show the decomposition where we have a square root monochrome image, and then we divide that from the target color image to get the color layer, and then physically these get multiplied together to show you this final high dynamic range image, which produces a peak brightness of about 20,940 nits and a instantaneous contrast ratio or checkerboard contrast ratio of about 80:1. So now I'll hand it over to Alex to talk about how we actually used this hardware to learn something about the requirements for HDR in VR.
Hello, everyone. My name is Alex Shapiro, and I will be presenting the second part of this presentation. So now Nathan has introduced us to the HDR virtual reality device that we have created for this project, and also gave us an intuition of what the luminance is like in the real world. But now we're going to start thinking about how to create a realistic luminance data set that really qualitatively represents various scenes in the world that are representative of everyday scenarios. And in order to do that, we start by looking at this data set called the Southampton York Natural Scenes data set, or SINS. And the good thing about this data set is that it has an excellent variety of indoor and outdoor scenes, which are representative of various everyday cases. And it also has high quality captures. It's captured in HDR using bracketed exposures with a specialist camera called the Sphere and HDR camera that records up to 22 stops without losing information, and also has accurate metadata capture for things like exposure values, aperture, and ISO, and so on. But one of the cons of this data set is that it does not natively have luminous information available. It only has the RGB captures from that camera. So in order to deal with that, let's first remind ourselves what is luminance. And luminance is a photometric, so seen by the human visual system, measure of luminous intensity. On this slide, we're showing the human visual response as defined by the color matching functions, in this case specifically the 1931 CIE standard observer. And the Y response is specifically the one we're looking for here, marked with the red arrow, which is thought of as luminance. Now, these here are the camera responses. And as you can see, of course, they don't match, the luminance response of the human visual system exactly, but this is the data that we have, and we'd have to try to recover the luminance from that if we're going to use this SINS dataset. And by way of example, here is one standard type of object. It's a Macbeth color chart, and shown below are the spectral reflectances of this color chart for each one of those colorful tiles. And with a dashed line, we show a standardized sunlight spectrum called D65. So if we were to try to predict or simulate what would be the camera response for one of those tiles, we would take the corresponding spectral reflectance, multiply it by the sunlight spectrum, and then by the response of the camera for each channel, then integrate, and that's how we would get our RGB values, or equivalently, we would do the same for the human visual system and get the Y values for luminance. Now, if all we have are those RGB values and we want to get Y, one method of doing that is relatively straightforward is this done by Finlayson and Drew in the maximum ignorance assumption with positivity method. And it's quite straightforward. All we would do is we would take our camera responses, represent them as vectors, and do the same with the visual sensitivities of the CMFs, and find the least square solution that just maps one to the other as well as possible using a 3x3 matrix as shown here. And you can improve on that slightly by also adding a positivity prior, which is essentially a preconditioner matrix, which keeps the method essentially similar but has better results on average. And so let's see what happens if we apply this method to that Macbeth color chart from the previous slide. And we will get a prediction that looks more or less like this. So the true Y values or luminance values would be the ones shown with the purple circles. And the reconstruction where we would first get the RGB values simulated and then use that 3x3 matrix that we've created in order to convert them to a predicted luminance value is shown with the X's and pluses for the maximum ignorance method and the one with the positivity prior. And we can see that although the results are not exact, they seem to be pretty good. They're pretty close to the true values. And for this work, we're mostly interested here in ballpark measures of estimates of luminance, not necessarily an exact measurement. So this seems to be leading us in a good direction. Now, one thing to note here is that these are all just up to scale, so they're not, their relative values. So in order to get values that are actually grounded in real world, physical units of luminance, we would need to measure some in the lab. So that's what we did, and we got that same sphere and HDR camera that was used by the SINS dataset authors. We took it into the lab, and we had an actual Macbeth color chart and also some standardized reflectance targets. And we measured them using this camera and also using a luminance meter, so we have these ground truth measurements from that device. Here are the results of the captures with the camera for different metadata, different exposure and aperture settings, and also compared to the reference. And now these have been converted using that 3x3 matrix from the previous slides into estimated luminance values, and then those can be adjusted based on the metadata using a simple exposure value formula that estimates how the metadata affects the results. And we can then see how that compares to the ground truth data shown here with the dashed blue line. And when we look at that comparison and we look at the relative error, we see that for most of the range there, especially for the higher luminance values, the errors are not too bad. They're in the plus minus 20% range. And this is also taking into account some of the measurement error from just our luminance meter and our lab setup that wasn't perfect. And for some of the lower luminances, there might be a little bit more error, maybe up to even 40% in the worst case. But we're generally okay with this kind of not fully precise measurement because we're looking more to understand what the real world is like rather than getting an exact measurement of it. Now, when we take this pipeline and we use our maximum ignorance estimation and our transformation matrix and our exposure value formula and apply it to the SINS dataset, which is that dataset of indoor and outdoor scenes, we would get something like this. And this is a histogram of all the luminance values reconstructed from a subset of the SINS dataset that is shown here, including 9 indoor and 10 outdoor scenes that we picked to kind of represent some real world scenarios. In this histogram, we can see some things that we kind of intuitively knew being shown. For example, indoor scenes are much less bright on average than outdoor scenes. And also outdoor scenes have these 3 sort of humps. And in this case, the humps are basically, the higher one represents typically the sky, and the lower ones are usually parts of the ground, which are not as bright as the sky. So now with this data, we sort of have a pretty good idea of what the real world is like in terms of luminance. And now what's left is for us to understand what are people's preferences for representing those values when seeing them in virtual reality. And so this leads us to our subjective study that we performed using our headset and using this SINS dataset. Before I start talking about our subjective study, I want to bring up one quick point of comparison for some prior art, which is this work from Dolby Laboratories by Dali et al. On the preference limits of the visual dynamic range. And what they did is they took this custom ultra-bright dual modulation display shown on the left, and they used kind of artistic Hollywood-style scenes shown in the center in order to run a study that was performed for both naive and professional audiences. And this study specifically was application-driven for cinema use cases, so it was kind of focused on relevant parameters for HDR rendering for cinema. So things like diffuse white point, dark level, and highlights specifically has to do with the way that colorists and directors and other creatives work when generating that kind of content. And the same was true for the experimental setup, where users were sitting in a dark room, simulating a cinema room. The screen was relatively small compared to a virtual reality screen in their field of view, and so on. So some things to point out about the study is, first, it posed a question of preference rather than, for example, a question of visibility, which could be true for different studies, which typically leads to more noise in the results or more differences in the results. And you can see that on the figure shown here on the right. And the other thing is the setup was highly geared towards cinema applications, like I just mentioned. So it opens up this question of whether these results will be valid for virtual reality, where you have a high field of view, you have tracking of the user, and the experience is pretty different from the traditional cinema experience. So this opens up for us this question of how does that cinematic preference that was set by Dolby compare to the realistic presentation that we're interested in virtual reality? So with that, we follow with our own study, which was consisting of 20 participants who are all naive participants. They used a method of adjustment procedure, which is actually analogous to the one used in the Dolby study. And it's illustrated here with this figure from the Dolby paper. The adjustment of luminance is done with a log mean luminance offset. And what this accomplishes is that it keeps the contrast of the image, static, while just making it dimmer or brighter. And we asked users to select the brightness level that feels most realistic or immersive for them. Specifically, they were working on those 19 SINS dataset scenes that we've studied earlier in the presentation. And they were asked to rate each one of them twice, starting from either the lowest or the highest possible mean allowed in our study, in order to see how that starting point would affect their answers. They were just asked to select the brightness level that feels most realistic or immersive to them. And so the pros of this is that it tests these important questions that we're interested in for VR, and also it's a relatively straightforward procedure. But the cons are that these realistic and preferred values are a little bit hard to pin down. For example, compared to visibility, can be affected by many variables, and so we expect the results to also have some range of acceptable values. And the other point to note here is that we did not explore contrast in this study, although of course contrast is very important for high dynamic range presentation. So it's worth thinking about for some follow-up work. Here is a video of our collaborator Romain performing in an initial version of this study. And you can see there he's using our prototype and making selections using the controls and the handles. This is a view of what he's seeing through the headset. There's a brief masking period that helps adapt and prevents direct comparisons, and some prompts for his answers. And here are the results of the study. On the x-axis, we have the sorted scenes, indoor and outdoor, and specifically they're sorted in terms of their ground truth luminance, shown here with the yellow squares. And one interesting thing to note here is that the indoor scenes were always dimmer than the outdoor scenes for this study. And that just kind of follows that intuition that the outdoors are usually much brighter in the real world. In terms of the experimental results, the dark circles show the answers that participants gave for the start high conditions, so when they were starting from the highest possible mean and essentially adjusting downwards towards their preference. And the light circles show the other case, where they start from the darkest possible case and adjust up towards their preference. The left side shows the indoor scenes, and one interesting thing to point out here is that the ground truth luminances were actually reproducible on the display for these scenes. And the right side shows here the outdoor scenes, and one interesting thing to note here is that some of these scenes you could not actually reproduce the ground truth luminances on our display, despite it having this outsized brightness capability. And this is because we did not want the scenes to clip at the top of the range and have large clipped areas. So we set a maximum permitted luminance of just under 3,000 nits. Here is a different look at those results, now in a linear space. And we've done here a separation between indoor and outdoor scenes, although no such separation was done in the study proper. So these differences are coming straight from the preferences of the users. And it's interesting how the users internally just preferred to set more luminance for scenes that were outdoor scenes than for the indoor ones, even though that wasn't specifically something that we asked them. So it's an interesting non-trivial preference. We also repeated the study in a pilot where we ran the images in color instead of black and white. And we got a result that was also pretty interesting. Specifically for luminance, on average, among all indoor and outdoor scenes, the selected level was about 443 nits, but for color, selected level was much higher at about 730. So this leads us also to some interesting thoughts about how color would affect the preferred levels of luminance in a headset. So with that, I'd like to say some quick conclusions for our study. So the first is that we generated a data set of real-world luminance estimates for indoor and outdoor scenes. We've created an HDR VR prototype that is capable of luminance over 20,000 nits while staying within a head-mounted form factor. And we also ran a subjective study that showed users have non-trivial luminance preferences in VR that are different from traditional displays. This is the end of our presentation. And I'd like to thank you for your attention and also point you to this QR code, which takes us to our GitHub repository where all the code and all the study results are available. And you can reproduce any of the methods used here and all of the plots that I've shared with you today. Thank you.